So let us start this session. In this particular session, let us try to have the coding of carry save adder. So previously we have discussed about the half adder, full adder, and what is your ripple carry adder, and what is your propagation delay, how much propagation delay you are going to have in the case of your ripple carry adder, and how if you are going to take a particular delays, like for sum is equal to 10 nanoseconds and carry is equal to 14 nanoseconds, what is the delay which we are going to take for sum and what is the delay which we are going to have for carry, we have seen. And we have also seen the difference between our ripple carry adder and carry save adder, like what is a ripple carry adder and what is a carry save adder, what is the disadvantage which we were having for a ripple carry adder, and how we are coming overcoming that particular disadvantage in the case of my carry save adder, we have seen. And also we have discussed about many things about triple carry adder, right? So if you haven't watched the previous session recordings, I recommend you to watch those particular session recordings. And also we have started with this particular carry save adder architecture we have seen, right? So let us try to implement my carry save adder code. So I'm going to declare a module which is carry underscore save underscore adder, carry underscore save underscore adder. So this carry save adder is going to have inputs as input 3 down to 0 A, B, and C are my inputs, and output I'm going to have as sum and carry, and output 5-bit result. So these are my inputs and outputs which I'm going to consider, and I'm going to declare few internal registers, few internal wires, 3 down to 0, CSA underscore sum and CSA underscore carry, which I'm going to take. Now, first of all, let us try to build this particular 4 full adders. Okay, so the for first full adder, we are going to give A0, B0, C0. Second full adder, we are going to give A1, B1, C1. A2, B2, C2, A3, B3, C3 to the last full adder. So that is what I'm trying to do over here. So full underscore adder FA1, I'm going to give A of 0, B of 0, and input as C of 0. So this is what we have given. And the carry and the sum, we are going to collect it using CSA underscore sum of 0 and CSA underscore carry of 0. This is what we have collected, right? And after that, we are going to write down next full adder, next 4 full adder instances we need to make. This is full adder 2, this is full adder 3, and this is full adder 4. And this is A of 1, and this is A of 2, and this is A of 3. And next is B of 1, B of 2, and B of 3. And over here, C of 1, C of 2, and C of 3. And this is sum of 1, next sum of 2, and next is sum of 3. And this is carry of 1, carry of 2, and carry of 3. Okay, now I'm going to assign the value of this sum. So assign sum is equal to CSA underscore sum, and carry is equal to assign carry is equal to CSA underscore carry. So this we have done. Now we have completed this particular first stage. So we have completed 4 full adder instantiations, right? Now what I'm going to do is, let me show it over here. Now what is happening over here is, we have got our sum and we have got our carry. Let's say sum is nothing but S3, S2, S1, and S0 is my sum. And this is nothing but 1, 1, 0, 1. And my carry I've got is C3, C2, C1, and C0, which is nothing but 1, 0, 0, 1. Let's assume it is 1, 0, 0, 1, right? Now what I need to do, I need to add this sum and carry. But here carefully, if we carefully observe this particular block diagram, we are adding the second stage sum with the first stage carry. So we are adding basically the second stage sum with the first stage carry. So that means we need to add this S0 with C1 S1 with C2 and S2 with C3. And this sum is basically added with the second last stage carry. So S0 is added with C1, S1 is added with C2. So let's assume this, we are going to get the sum as S3, S2, S1 and S0 and C3, C2, C1 and C0. Okay. Now here we need to add my sum and carry, but here if we carefully observe in this particular block diagram, we are adding this sum, we are directly taking the sum and the second stage sum is added with the first stage carry. So over here, this particular sum should be added with C0 and this sum is added with C1 and this sum is added with C2 and C3 is added with 0. Okay, and this sum is not added with anything, you can see over here. So what I'm going to write down is I'm going to take a 4 bit carry C4, C3, C2, C1, C0 and I'm going to left shift the original carry. I'm going to perform the left shift the original carry. So that let's say if my C3, C2, C1 is 1101, it becomes 11010. This is the left shifted version of my original carry. Now what I'm going to do, I'm going to add S0 with C0. It will be the same now. So instead of you adding, if instead of you taking S0 directly or adding S0 with 0, I'm doing the same thing because if we are left shifting, obviously the LSB bit will be 0. So that's the reason I'm adding S0 with C0. S0 with C0 I'm adding and S1 I'm adding with C1. That means indirectly I'm adding S1 with C0. Okay, so that's the reason I'm adding S1 with C1 and H2 I'm adding with C2. That means indirectly I'm adding H2 with C1. So H2 I'm adding with C2 and S3 I'm adding with C3. That's it. And C4 I'm adding with 0. That's it. So this is what I'm going to do in my code. So first I'm going to make the left shift operation. So for that I'm going to take a variable of 5 bit 4 down to 0. So here it is 5 bit 1, 2, 3, 4, 5, right? So I'm going to take a variable which is carry underscore shifted and I'm going to assign carry underscore shifted which is equal to CSA underscore carry comma 1 tick binary 0. This is left shifted version. Now after making this, I'm going to take few wires, wire C1, C2, C3 and C4 and one more wire 4 down to 0 final underscore sum. Okay. Now I'm going to take again 4. I'm going to take again 4 full adders. So I'm going to, I mean 5 full adders. So I need to add all this, right? So this triple carry adder, I need to build it now. Okay. Not 4-bit triple carry adder we are going to take over here. We are going to take 5-bit triple carry adder. We need to have a 5-bit triple carry adder over here. Why we need to have a 5-bit triple carry adder? Because we can see S0 C0, S1 C1, S2 C2, S3 C3 and C4 plus 0. For this we need a 5-bit triple carry adder. So let's build a 5-bit triple carry adder over here. Full underscore adder FA0 or let's say it as CPA0. Okay. And next is let me copy paste this particular thing. Okay, so I took 5 full adders. I'm going to build a 5-bit triple carry adder, right? Now for the first thing, I'm going to give the sum as the argument. CSA underscore sum of 0. I can see over here. So I'm going to give CSA, whatever the sum I'm going to give, get, I'm going to give it to the first argument. Over here, it is not shown. Actually, this we can extend it. Let me show you. Here we are extending basically. Let me draw it over here. So we are extending and this sum is basically added with 0. That is what we are doing. Okay, so that's the reason we are going to have 5-bit full add. So see, this sum is basically added with CSA underscore carry of 0. That means I'm basically adding 0. Okay. And next is the initial input Cin will be equal to 0. And output which we are going to get, that I'm storing in my final underscore sum of 0. And carry I'm going to store it in my C1 because I'm building a ripple carry adder, right? And let me copy this and paste it over here. So this is CSA underscore sum of 1, and this is CSA underscore carry of 1. And over here, the first stage carry which we are going to have is C1, that I'm going to give it over here. And final underscore sum of 1 and C2. So this is what I've done over here, right? And let me paste it over here. This is CSA underscore sum of 2 and CS underscore carry of 2. And the second stage carry, I'm going to give it to the third input. And this is final underscore sum of 2. And this is C2. I mean C3. Next, here, let me copy paste. So this is CS underscore sum of 3 and CS underscore carry of 3. And this is C3 I'm going to have. And this is C4. And here I need to write C4. And this is final underscore sum of 3. And here I'm going to get C out. That's it. So this is how I'm going to build. And for the last stage, my first input is connected to directly 0. And second input is connected to my CSA underscore. I mean, I need to use carry underscore shifted version, not CSA underscore carry. My mistake. Because previously only I have told you, right, I'm going to add the sum with the shifted version of my carry. Okay. So CS underscore carry underscore shifted of 4. Okay. And this sum I'm going to collect it, and the input carry is basically C4 I'm going to have. Okay. So it is C1, C2. Here I'm going to have C3. This is C2. Okay. And here C3 and here C4. And here I'm going to have C4, and the output I'm going to collect it in my final underscore sum of 4. And my output is C, right? This is how I'm going to build the 5-bit triple carry adder over here. That's it. And followed by end module. So this is how I'm going to build a simple carry save adder. So before that, I also need to have the full adder instance that should be created. So I've already declared the full adder over here. Okay. So the full adder instance that should be already created, that should be present over here. Okay. Yeah. Now let me save this file. Yes, the file has been saved, and in the test bench, let me check what is. So this is a test bench which I've written over here. And in the test bench, let me check what is the name I've given. Carry underscore save underscore add underscore 4-bit. Let me copy and give it over here. Carry underscore save underscore add underscore 4-bit. Yes. Let me save it. Yeah. And test bench also I've written. Test bench is very simple. Just declare the inputs as rich and outputs as sum and carry and result. And I've instantiated my design, that is carry underscore save underscore adder. Next, I have written a task for driving my inputs, and I have driven multiple inputs like 000, 001, 111, 15, 15, 15, 1500. Like this, I have driven multiple inputs. Okay. I'm just adding the three numbers or variables. Let me run the simulation and let us check the output results. Let me check. There is some error over somewhere. Okay. Here carry is missing. Let us check whether I've declared. Yeah, this is capital C. And let me rerun it again. Okay, I think we have done some mistake while instantiating the things. Let me check it out. ABC, sum carry, and result. In the test bench, ABC, sum carry, and result. Let us check it out what we have done over here. ABC, sum carry, result. Okay. This particular sum, we need to check it out whether we have declared it or not. And carry also. Yeah, carry we have written. Yeah, let me rerun it one more time. Let me rerun it. Over here, my sum is of 4-bit width, right? So I need to declare it as a 4-bit width. That's the error I'm going to get. Save it and run the simulation again. So since only we have declared it as 1 bit, out of 4 bits, only 1 bit is being connected. That's the error. So that's why it is showing unconnected state. Yes. So let us check it out. And result we haven't connected. So result we are going to result also let us connect it. So assign result which is equal to final underscore sum. Let me save it and let me relaunch it again so that let us check it out what is that we are going to get. Yes, so this is what we are going to get. So we can see over here, let me zoom in a little bit. So 8 plus 0 plus 8 plus 7, which is nothing but 15. So this is nothing but my result I can see over here. Or else if I'm going to get d plus 2 plus 1. So I can see over here d plus 2 plus 1, which is nothing but 10, 1 0. It is not 10, it is hexadecimal. Okay. And e plus e, we are going to get the result as e. Okay. So this is how we are going to uh, e plus e, which is nothing but a. So this is how we are going to implement a simple carry save adder design and test bench. Okay. So the main advantage of this carry save adder is you are going to have more number of input operands as well as the delay which you're going to consider over here is less, which is compared to your ripple carry adder, which we cannot find it out in the simulation. The delay thing which we cannot find it out in the simulation, but it can be find it out in analysis, static time analysis. It can be find it out, right? Yeah. So that's about the day one, that is project one in this particular series. Next, we are going to start with other project that we will discuss. Okay. Yeah. Thank you.